We're going to continue talking about energy and muscle function. So in the last lecture, we talked about the fact that myoglobin and creatine phosphate are two really effective ways which our body can deal with a lack of energy when you're going through vigorous exercise. Whether it's running from an animal, as originally intended, or chasing an animal to eat it, or just going to the gym and exercising like we do today because humans have technology. But either way, there needs to be some avenue to get energy if you run out of energy. Which leads us to the next discussion. What about normal circumstances when you're not running out of energy? And that leads us to this idea of aerobic versus anaerobic respiration. Now, I'm not going to spend a lot of time on this because you learned this already in biology class. But what I want to do is we do need to talk about this idea of anaerobic respiration because it happens a lot in humans and there's an issue that occurs from it. So what does aerobic versus anaerobic mean? It simply means, is oxygen present or not? So anaerobic means oxygen is not present, and aerobic means oxygen is present. So if you take a look at this diagram here, this is not something I'm going to hold you responsible for. However, it's a quick review of the difference between the two. So just remember, this happens in the mitochondria. But in order for the mitochondria to do its job, it needs oxygen. So for example, glucose is what our body uses as fuel. When glucose is present, we use glucose. When glucose is not present, we use glycogen, which is that sugar that's stored in our liver, and it gets converted to glucose, which will come up again later in this lecture. Having that said, normal circumstances, glucose has 6 carbons, right? So glucose goes through this process. And the first thing that happens is it goes through this glycolysis. And glycolysis is when you break that glucose down into a 3-carbon sugar called pyruvate or pyruvic acid. Now, this is something that you learned about in biology class. At this point, one of 2 things happens. If oxygen is present, it will go into the mitochondria, go through the process of the Krebs cycle and the electron transport chain, which will lead to the production of 34 ATP, with addition of the original 2 that you get from glycolysis, you get 36 ATP. So for 1 glucose, you get 36 ATP. This is ideal. This is the ideal scenario. This will provide you with enough ATP to have your body function. But let's say there's not enough oxygen available. That leads us to something called anaerobic respiration. And that can happen one of 2 ways. One is through alcoholic fermentation, and the other one is through lactic acid fermentation. We cannot do alcoholic fermentation. That does not happen inside of our bodies. Now, there are some instances where that does happen. There are some mutations that occur where certain bacteria in somebody's gut will cause alcoholic fermentation. So when you eat sugar, you get drunk, which might sound great on paper, but imagine if you couldn't control it. Now you don't want to be in that state all the time. So thankfully, that's not something we deal with. However, we do deal with lactic acid fermentation. That is a common occurrence in our physiology. Because if you're exercising vigorously, at a certain point, you're going to run out of oxygen. And your myoglobin will step in to provide extra oxygen, but you're going to burn through that quickly as well. And at that point, there's no more oxygen there to use. So what ends up happening is you start to go through this process called lactic acid fermentation, which happens in your muscles. And what that does is it essentially allows this first step to keep continually going. So you can keep producing 2 ATP for as long as you're producing lactic acid. And it's a great solution. It gets you just the energy you need to finish the exercise, if we're talking about exercise, or more realistically, to get away from whatever animal is chasing you. So lactic acid fermentation is an example of anaerobic respiration. It will not allow you to, you can't live off of this, but it will give you the energy you need to get you out of trouble. Or, like I said, in the case of exercise, you might get that last burst of energy to beat somebody in a race. So let's talk about the problem with that, though. So when you have this situation occurring, what ends up happening is you have this original thing where glucose goes and becomes pyruvic acid. That gets you your 2 ATP. And then you go through this process called the citric acid cycle and the electron transport chain, which gets you 34 ATP. Here is the problem. The problem is that if you start to produce lactic acid, let's say you don't have oxygen available, you're going to just keep going through this initial stage here called lactic acid fermentation. And you can keep churning out ATP. You can keep working. If you've ever worked out before and you feel a burning sensation in your muscles, you will continue working out and you can keep going until at a certain point your muscle fails you. And when your muscle fails you, that is because you have too much lactic acid build up in your muscles. So how does our body get around that? Well, what ends up happening is the blood gets carried to your liver, and your liver can actually convert lactic acid back to glucose. It's pretty amazing, right? So your liver can take lactic acid and convert it back to glucose, and then that glucose can get used to make more energy. Here's the problem though. That requires energy. So the act of using up that lactic acid and converting it to glucose in the liver, that costs energy. And that leads to a concept that I need to explain today called oxygen debt. So it's a little bit confusing, so I'm going to explain it, and then hopefully it makes some sense. One other thing that you can see on this slide is it just brings up myoglobin over here. So that's this little comment over here is because when you're exercising, for example, when I'm lifting a weight, my muscle's going to contract. It's going to actually push on my blood vessels and decrease the amount of blood flow. That's one of the other reasons why myoglobin is helpful in a muscle contraction. When your muscle's actually contracting, it is putting pressure on the blood vessels and decreasing the blood flow to that muscle. So myoglobin is not just there for when oxygen is in short supply, it's also there because when your muscle actually contracts, it causes a short supply of oxygen. And that's just what this little piece over here says. So basically what ends up happening as lactic acid accumulates, you get something called oxygen debt. So let me explain oxygen debt. The word debt means you owe it, right? So for example, if I'm in debt money-wise, I owe money to somebody. I borrowed money and now I have to give it back. Oxygen debt is the same concept. If you've ever worked out hard, you know that when you're done, you do a lot of this, right? Right, you're out of breath. And the reason why you're out of breath is because you're trying to repay your oxygen debt. So let me explain this and then hopefully it makes some sense. Okay, so here's the explanation. When you exercise a lot, what ends up happening is you have a decrease in oxygen, which leads to lactic acid buildup. So I'm working out, and then all of a sudden I start to feel burning sensation in my muscles. What that means is I've run out of available oxygen, and I'm now producing energy through lactic acid fermentation. And here's the problem with that. The more lactic acid I build up in my muscles, the more I'm going to have to process through my liver to get it back to where it needs to be. And that requires energy. So what does this mean? What this means is basically strenuous activity leads to deficiency of oxygen and lactic acid buildup. You need energy to provide a muscle contraction. You require ATP. So here's what ends up happening. If the amount of oxygen that needs to be converted back to lactic acid and is going to build up in those muscles, that is what your oxygen debt is. So the more lactic acid you build up, the more oxygen you need after the fact to produce ATP to convert it back to glucose. So the more lactic acid you build up, the more energy you need after the workout to convert that lactic acid to glucose so it's usable. And that's what this last bullet point says here. So the lactic acid leads to muscle fatigue because if the acid if the pH drops low enough, the muscle can't contract anymore. So your muscle will not function while it's in that state. So you need to build up those levels again. So oxygen debt very simply means when you use all of your available oxygen at that point and you convert to lactic acid fermentation, you're going to be using that for as long as you can. But the more lactic acid you build up, the more you have to convert back to glucose later. And that requires energy. And that is called oxygen debt. And that is why after you run really hard or sprint or anything like that, you feel out of breath for several reasons. But one reason is because you're trying to rebuild that oxygen debt. You're trying to get enough oxygen into your system to create energy to convert that lactic acid back to glucose. That is oxygen debt. Okay, the last couple things I want to talk about here. What is a muscle cramp? You've all experienced muscle cramps before, right? You're working out and then your muscle locks up, right? You're running hard and all of a sudden, oh my God, my calf just locked up. Why does that happen? Well, it can happen for a couple reasons. One of the main reasons is it requires ATP to pull the calcium off of the troponin, right? So if there's not enough ATP to pull the calcium off of troponin and to back into the sarcoplasmic reticulum, those muscle fibers are going to stay contracted. So even when you want to relax it, it's going to stay contracted. Also, if there's not any ATP left to move that myosin head from the actin. So that's what a muscle cramp is. Essentially, the myosin and the actin head stay attached to each other. The tropomyosin is not able to be pushed back into place. And that can happen for two reasons. One, the ATP is not available, and that will cause the myosin head to stay attached to the actin. It would also cause the calcium to not be able to pull back into the sarcoplasmic reticulum to break the tropomyosin bond. Either one of those, you have two options with a muscle cramp. How to get rid of a muscle cramp? One is you sit there and wait, and if you sit there and wait, you'll rebuild your ATP stores and your muscle cramp will go away. Or you can actually massage it, because remember, this is a physical thing, right? That myosin head is actually attached to the actin. So if you take your hands and massage that muscle, or use one of those rollers that you can use, that will actually break that bond and the muscle will relax. So a muscle cramp is caused by a lack of ATP, and that causes the cross bridge to stay intact and that muscle will not relax. Which leads us to our final piece of notes for this lecture, and that is something called rigor mortis. Rigor means stiff, mortis means death, and that is what happens when something dies. All of the muscles in that organism actually lock up and they stay in a contracted form, and that's why they call, you may have heard this before, slang for a dead person is a stiff. And that is actually how they can determine how long somebody's been dead for. Because if they are still in rigor mortis, they know it's only been, a certain amount of time since that person has died. And then eventually the body starts to break down. But why does it actually happen? This is pretty bizarre. What ends up happening is once something dies, something happens. The sarcolemma, or the cell membrane, starts to become very, very, very permeable to calcium. So essentially the calcium doors just open and calcium floods into the muscle. So you've basically taken away the control of being able to control your muscles. That sarcoplasmic reticulum doesn't matter anymore because calcium just floods into the muscle. And when calcium floods into the muscle, it attaches to the troponin and the myosin head attaches to the actin. But here's the problem. When something's dead, it can't make any more ATP, so there's nothing to break that bond. So essentially what happens is with rigor mortis, all the muscles in the body, it's not one muscle, it's all the muscles in the body. So every single muscle contracts because calcium just floods in. There's no control over it. Those muscles contract, and then there's no ATP because when you're dead, you can't make more ATP. It just stays contracted, and eventually it will, the muscles will start to break down, and that's what makes them relax. But this could take up to 72 hours to occur. So if something dies and it's not in rigor mortis yet, they can tell how long it's been dead for. It hasn't been dead that long if it's not in rigor mortis. If it is in rigor mortis, they know that it's been dead for at least a couple days because it takes that long to get to that point. And that is all.